do them, and also thinking about the, as we analyze some of these questions, you can start to see where some questions can be pretty relatively simple. I think the ones we did yesterday, like this guy got 8 hits in 10 games, that's pretty simple. It's kind of elementary. I don't think the end of course exam is going to ask something about ratios like that. They're probably going to ask something more like this. This is called a capture-recapture technique that actual biologists and conservationists use to determine certain populations of animals. Okay, if you think about it, if you've ever, anybody interested in like endangered species or anything like that, no matter what like endangered species you like research, they will tell you this is an approximation of how many of these animals are in the wild, right? Okay, if you look up like black rhinos or white rhinos or whatever, they'll tell you that, hey, we think that there's 35 of these animals in the wild or something like that. They didn't call a census and ask all the rhinos to show up to a meeting so that they could count them, right? Like, that doesn't make sense for them to be able to do that. So they use what they call a capture-recapture technique. And what happens is, and we're going to use rabbits for this particular situation, there's this situation called Briar Lake National Park. They want to go and figure out how many rabbits does this environment have. So what they do is they go out and because they have no knowledge of the overall population of rabbits, right? So they go out and they capture as many rabbits as they can find. And in this first capture, they find 900 rabbits. And they put tags on them, tags in their ears, okay? And what that does is it sets an initial population for them, okay, for what we call our second recapture, okay? So they they tag these 900 and let them go, okay? Then they go out a second time, and they capture as many rabbits as they possibly can, okay? It might be close to 900, it might be more than that, it might be less than that, okay? But once they go and recapture the second amount of rabbits, some of them are going to have tags, and some of them will not have tags. Does that make sense? Okay. Now, if they didn't, let's say they go out the first time, they capture like 3 rabbits and put tags on 3 rabbits, and then they go out the second time and they get 100 rabbits, but they didn't find those 3. And the reason for that is because the first sample of 3 rabbits was not enough to model the population. Does that make sense? So they need, in this case, 900. So in the second capture, they go out and in this case, they said they captured 200, okay? 2,000. Of those 2,000, 6 of them had tags, okay? So those 6 that have tags, okay, were out of 900, right? Okay? Which, when they collect the 2,000 then, after that, we can use ratios, proportions, to kind of get an estimate of how many initial rabbits were able to be collected in that first capture. When we got 900, how many was that 900 really out of? Does that make sense? So I'm going to set up a proportion. There's a couple different proportions you can make here. And if you Googled like a capture-recapture process or something like that, you might get like a breakdown of the actual formula that they always use in this situation. And I think I talk about this in my integrated class. I don't remember what section it is, though. Might not be able to find those. But I've got an explanation of that somewhere, of the proportion that they always use. And after we come up with a setup here, we'll talk about the varying proportions that you could generate. So what I like to do is I like to know that I'm going to have 2 ratios, okay? So I'm going to collect 900 rabbits. I'm just going to label it with tags, 900 tagged rabbits, okay? And understand that we're trying to figure out the entire population. When I tag those 900 rabbits, I don't know how many of those came from. Does that make sense? I don't know. Maybe there was only 900 rabbits. I don't know. Maybe there's 902 rabbits. Maybe there was 10,000 rabbits. I'm not certain how many that 900 came out of. So I'm going to put 900 compares to an X population. I don't know the total number of rabbits that came from. Does that make sense? Now, when I look at my second ratio, and this is something I talked about previously, when we write proportions, and I think we did this with the model airplane question, I want my numerators to have a relationship. And I want my denominators to have a relationship. Okay? So the relationship that I always keep consistent with my numerators and denominators is their units. Okay? So I'm going to put tags on top up here, and I'll put population down here. So that first ratio was the capture. The second ratio is going to be the recapture. How many tags did I find in the recapture? I had 6, right? Those 6 tags, those 6 rabbits that had tags on them, came out of how many rabbits in that second capture? 2,000. Does that kind of make sense? So what we do here, if we count, and then there are, if you get into like biology and conservation in college or whatever, there will be, and it couples with a stats class, you will talk about, okay, how do I know that this is accurate? Okay, and there's a certain amount of sample size that you have to basically have some confidence that this result here is accurate. Okay, so maybe 900 is enough to say that the results that we get here are pretty accurate. Okay, where if I would have gotten just the 3 that we talked about earlier, obviously that's not enough to produce an accurate result. Okay, but now if I cross multiply, I get 6x. Lost my cursor. There we go. I get 6x equals. Now, when I do this stuff, I'm not going to multiply, guys. I think it's, I don't know if I said this yesterday, I think it's foolish to actually multiply 900 by 2,000 and then divide by 6, because you're going to amplify something and then reduce something, right? So you're going to undo that multiplication somehow that you just started with. So I'm going to do this. I'm going to divide this by 6, okay? And when I divide by 6, would that be equivalent to dividing this by 3 and that by 2? Is that still dividing by 6? That kind of makes sense. I just kind of use my associative and commutative properties kind of to my advantage there. What's 900 divided by 3? 300. And now what's 2,000 divided by 2? 1,000. So now I've got 300 times 1,000, right? And that 3 times 1 is 3, and I've got 2, total of 5 zeros. So it gives me x, and remember what we let x be. X was the total population that initial 900 came out of. So when I went out that first time, and I got 900 rabbits tagged, and I had no idea what the population is, now I know that population that 900 came out of was actually 300,000 rabbits. Okay? Does that kind of make sense? So when you see, when they tell you on those endangered lists, or they talk about a lot of times at this time of year, about a month and a half ago, they start talking about deer populations in Ohio, right? Okay, because deer season, correct? They don't survey every deer and go ask them, hey, can you fill out a census so we can collect data on you? Okay, they use this type of stuff. Okay, they'll collect information. Maybe they'll go out in certain counties and tag so many deer in a certain county, and then go back out a second time, recapture them, and get county populations, and then they kind of accumulate those for the state or something like that. Does that make sense? So that I like to show questions like this because it gives you. I always have the question, what is math good for? Okay, that's a. Hopefully you guys think that animals are important and conservation is important maybe. I think that'd be an application that we can see actually demonstrates the use of math in a beneficial way. This one, I don't know if there's any benefit of eventually ever doing this. Okay, it's kind of like one of those basic story problems that you're thinking, okay, why would I ever care about how many marbles Jane and John have? But I want to demonstrate this one because these are more difficult type ratio questions, or proportion questions. There's a lot of different ways that we can approach them and deal with them. Okay, even this last one, I know I'm going back here, but this last one, you guys remember talking yesterday that it was okay if I wanted to take these two things and interchange them. I could have said 900 tags in the first situation compares to 6 tags in the second, just like the X population, the overall population, compares to maybe my sample population that second capture. Does that kind of make sense? You could do that. That will still give me 300,000. Okay? You can even interchange these two, that one and that one. Okay, but here's my thought. If I do that, I get 200,000 over X equals 6 over 900. Is that just the reciprocal of that one? And then use the symmetric property to flip it. But so you can interchange the means, interchange the extremes. You could do, I don't know that anybody would do this, but yesterday we talked about how we could take 900 plus X over X equals 2006 over 2000. We could add that denominator to that numerator, that denominator to that numerator. Cross multiply, I'm still going to get the same result, 300,000. Okay. I would think that most people are going to, if they didn't do it the initial way that I walked us through it, you'd probably come up with that what's in that purple box. And I always get the question, okay, I got the same answer. Is it okay that I did it this way? Well, from what we did in class or what I gave you with a response of how to do this problem, does your work get created by interchanging my means, interchanging my extremes, or adding my denominator to my numerator? Does that make sense? Or we're looking at reciprocals. Any combination of those things will generate a legal proportion that will still give you the same results. Is that okay with everybody? So when you ask that question, and the reason I say that is somebody will ask us, we did this problem. I'm going to do this problem the same way we did in the class last period. But then they ask, well, can I have just done this? Can I have just done this ratio, this comparison? And the comparison they gave me, much easier. But to analyze whether yes or no we can do that was to see if my work, if I maybe add my denominator to my numerator, generated what they had. Okay? And then that would argue, yes, you can do that, or no, you can't do that. Okay? So this one says John has 30 marbles, 18 are red, 12 are blue. Jane has 20 marbles, some are red, some are blue. Says the ratio of red marbles to blue marbles for both of them is the same, so that's important. Okay, so when it says that the ratio of their blue marbles to red marbles is the same, that tells you can set up a proportion here. You got two ratios that are equal. Okay, if this is the case, then John has how many more blue marbles than Jane? What I like to do with questions like this, and I do this with all story problems, I take out the pertinent information. I'm going to write down here that John has blue marbles and he's got red marbles. His blue ones are 12 of them, right? And 18 red. Jane, she has blue marbles, she had red marbles. Okay? Now here's where the problem kind of starts to get a little bit confusing. We don't know how many blue marbles or red marbles she has, right? So what should I let one of those objects be? If you don't know, let it be X, right? Okay. Now, and then here's the case. It doesn't matter which one's X. I'm going to let blue be X, okay? But it doesn't matter. Now, before you answer this, just think before you answer it. If I know my blue marbles are X, I should now know what my red marbles are. Don't answer it with Y. Y would not be entirely wrong, but when you set the proportion up, you're going to get an equation that you can't solve because you don't have two relationships here. You would need another relationship with X's and Y's to be able to solve that. Do you know how many total marbles she had? she had 20, right? So can I go 20 minus X? That kind of make sense? Okay. So here's the idea. It says that they have the same ratio of red to blue. So if John's red to blue is 18 to 12, her red to blue should be that, shouldn't it? That kind of make sense? Now if we cross multiply, I get, I'm going to simplify real quick. Those both divide by 6. So I get 3 halves instead, just to make my multiplication a little bit easier. So I get 3x, when I cross multiply those, and that's going to give me 40 minus 2x. Oh, I did this right. Blue. So right here I've got red to blue here, right? So we got red to blue, right? Okay? All right. Add 2x to both sides, you get 5x equals 40. X is 8, right? So she has 8 blue marbles. She has 12 red marbles then, right? Okay. The key thing here is to make sure that you, when you kind of define your variables, I'm being descriptive with what X represented, right? If I don't write that stuff down there, and maybe I let X be the red marbles and I get done, I got 12, I don't know what to do with that 12. Does that make sense? But because I've labeled things, I know X is 8 here. So now it says, how many more blue marbles does John have than Jane? I can compare the 12 and the 8, right? So he's got 4 more. All right. Now, somebody in the last class said, well, could we have done this? Could we have just compared John's red marbles to Jane's red marbles? So his red ones to her red ones, and then his blue to her blue, which was X, right? And the question is that okay? Well, if we go back to what we started with, stuff in the background that I've got hidden there that I don't want there. If we go back to this, that way. If I take that one there and that one there and replace them, interchange them, switch them, does it create that? Does that make sense? So that's okay. This would have been fine. You can compare red to red, blue to blue. And the way that, I told you I like to keep my numerators so that they're linked with one another, okay? Well, the linkage here between numerators would be red and red. The linkage between denominators would be blue and blue. And the link 18 over 20 minus x, okay? 18 and 20 minus x, I guess actually that would be, let me rephrase that. Think about this way. So 18 would have been John's red ones. So let's put John's red ones. 20 minus x would have been Jane's red ones, right? These would have been John's blue ones. The cursor died. 1 second. Here. This would have been John's blue ones. And this one would have been Jane's blue ones. So the link here across the top we've got all of John's marbles. Across the bottom, we got all of Jane's marbles, so that's the link between numerators and denominators. The link between this ratio here is that we're looking at red marbles, right, in that first ratio. And in the second ratio, we're looking at blue marbles. It's a little bit different comparison in here, but as long as there's a link, it allows you to set these relationships up correctly. Does that make sense? Okay. But somebody said last period, they said, can we take, I think they had, what did they do? They asked me if 30 over 18 equals x over 20, I think. They asked if something like that was okay. And my argument was, well, if we take what we started with, 18/12 equals 20 minus x over x, okay, I'm going to find the reciprocal real quick of this. So I get 12 over 18 equals x over 20 minus x. I guess their question was something like this, maybe. And they said, can we get from this to that? Well, I find the reciprocal. Now I want to add this 18 to the top. So I get 30 over 18 equals, now I want to add this to the top. So I get x plus 20 minus x over 20 minus x. I guess that's what I had them in a 20, sorry. But when they do that, so do these x's cancel out? I get 30 over 18 equals 20 over 20 minus x. And I guess that was the proportion. They asked me, was that okay to come up with? Well, if I do that, okay, that was finding reciprocals, which we said yesterday was okay, and it was adding denominators to numerators, which said that was okay. And that's what we generate. So that is going to produce the exact same answer as what this original proportion that we came up with created. Does that kind of make sense? All right. So as we do things in class, and this is one of my pet peeves with mathematics in general, is people always ask, show me the one way, or do it this way because that's the way I've memorized or I've learned how to do it. But there might be 3, 4, 5 equivalent satisfactory ways of doing it. Okay. So I want to make sure that we at least touch base on some logic of why maybe you can get to the same answer. Hunter?
I had 30 over 12 and 20 over x.
Okay, so you went, give it to me again. 30 over 12 equals 20 over x. Okay. So I started mine with, I had 18 over 12 equals 20 minus x over x. So if I take and add 12, add that denominator to this numerator, right? Does that give me 30 over 12? And I'm going to add this denominator to that numerator. Does that give me, do those cancel out and leaves me just 20 over x, right? So because I start with mine and add the denominator to the numerator, this is perfectly fine. Okay? And if we cross multiply, okay, that factor of 10 is going to cancel the factor of 10 there, right? This factor of 3 is going to cancel the factor of 3 in there. So I'm going to be left with x equals 2 times 4, which is still 8. So absolutely makes sense. The only thing that I would be cautious of is remind yourself you somewhere labeled what x represented, right? So hopefully you labeled that x represented the number of blue marbles that Jane had. Does that open your eyes, guys, to multiple ways of doing these? Okay. I prefer, because I know it's not going to ever create issue for me in the problems that we come across, I prefer to do things like this algebraically. Set them up this way. Now, the algebra might be a little bit messier here, Okay? But the logic to how I set it up makes more sense to me than maybe making something like this. And it's up to you, though, however you want to approach it. This one's hard. This one is, the algebra is not all that difficult, okay? But the logic doesn't make a whole lot of sense initially, okay? And we read this, it kind of sounds like a Dr. Seuss question. It says there are 50 people in class. Some speak English, some speak Spanish, some speak both English and Spanish, some speak neither, okay? So you got speaking, or Spanish and English speaking students of all types of abilities, okay? Says we got 50 people. Says if we know that 30 of those people speak English and 20 of them speak Spanish and 5 of them speak neither, can you come up with the ratio of those who speak Spanish and English to those who speak neither? Okay? So here's the problem. If I look at the data they give me, the number of people that speak English is 30, right? The number of people that speak Spanish is 20. The number that speak neither is 5. And the amount that speak both isn't provided, right? And here's kind of the process that we have to go through, okay? When I tell you that 30 people speak English, and that's all I tell you, do you know anything about those 30 people and whether they speak Spanish or not? No. So some of those 30 people could speak Spanish, but all I'm telling you is that I know something about their English skills. And when I tell you that somebody speaks Spanish, or 20 people speak Spanish, I don't know. Some of those might speak English as well, but that 20 says, I just know they speak Spanish. Does that make sense? Okay? So what I'm trying to argue here is that there might be some people in this 30 that speak English. Obviously, all of them speak English, but there's a couple in there that might speak Spanish too. And here, all 20 of them speak Spanish, but there's going to be a couple intermixed in there that speak English. Does that make sense? If I add these three numbers together, what do I get? 55, right? How many people are supposed to be in my class? 50. So how many people got added in here and in there as an English-speaking Spanish person or Spanish-speaking English person? 5. Does that kind of make sense? Okay. That was the excess of people when we added these. So that must mean that those 5 got counted twice. In here, in this 30, and in this 20. So the fact that we've got now 5 people that we logically know speak both languages. Okay? So then when they ask you, well, what's the ratio of people that speak both to the people that speak neither, it's now 5 to 5, right? Or 1 to 1. Okay? Have you guys do probability at all last year in Algebra 1? Or at all, maybe 8th grade, 7th grade? You guys know how many cards are in a deck? A deck of normal playing cards? 52, okay? So let me just pull a picture up here real quick to kind of explain what we just did, but in maybe a format that you are maybe more familiar with, or that you can visually see kind of the components of the question. And we'll do this later on. Here's your deck of cards, okay? We got 52 cards here, right? Okay. Now the question I'm going to ask you is, what is the probability, so I'll say capital B for probability, of picking an ace or a red card? Okay. And we'll talk about this later on in chapter 13. But how many aces are there in a deck? 4. Okay? So we got 4 aces out of 52. Okay? Now the word or means union, which we've talked about a little bit with inequalities, and it means and to us, or not and, it means addition to us in probability. How many cards are red? 26. Half of them are red, right? So if I add those together, I get 30 over 52, correct? But that probability is not the probability that I hand you a deck of cards and say, what's the probability you pull a red one or an ace? That probability is higher than what the actual probability is. Okay? Because when I look at that 4 out of 52, did these 2 cards count in that 4 out of 52? Because these were my aces, right? This is my column of aces. So these got counted in that probability. Did these 2 cards get counted as those red cards? Does that make sense? So those 2 got counted in there as well. Okay? So what we're doing, if we leave it this way, is that we're making it more likely that these 2 cards get pulled than what should happen. Okay? So we need to remove those 2 cards. Does that make sense? One time. They were added in here. They're added in here. We only want them added one time total. So I'm going to subtract 2 out of 52. And that's going to give me 28 out of 52 to be my probability for picking a red or an ace. Those 2 events are said to be non-mutually exclusive events. You ever heard that phrase before? When things are mutually exclusive, they cannot happen at the same time. Okay? So let's say, like being awake and being asleep. Those are mutually exclusive events, right? You cannot be doing the same thing at the same time. Okay? Here, these are non-mutually exclusive because I can pick a red card or an ace inside one pool. Does that make sense? It can happen at the same time. The idea, the reason I'm explaining this is that's what's happening right here. Okay? You can have an English-speaking person that also speaks Spanish, or a Spanish-speaking person also speaks English. Okay? So they are not, in this situation, they are non-mutually exclusive events. So when we recognize that, we have to realize that we have to remove, they've been counted twice, and you need to remove them one time. Okay, so they only get counted one time. Does that kind of make sense? All right. Let's go to that worksheet that I gave you. That's not due yet. I want to make that worksheet due tomorrow night. We'll talk about that here in a little bit. But are you having any trouble with the factoring questions up top? Anybody want to do any of those?
Should we be getting answers for each one, and then we find out what the number was, or like
well, so they should all work. We can do one. Which one? I don't want to do the 4 or 5 that I gave you yesterday. So let's use one of these over here in this column. Let's just go ahead and do that top one. Okay. So that's a proportion, right? Okay. By definition, a proportion is a ratio equal to a ratio, right? Left-hand side's ratio, right-hand side's ratio. So can I cross multiply? If I cross multiply, we get x minus 3 times x plus 5 equals 20, right? So that times that gives me x minus 3, x plus 5, and 4 times 5 gives me 20. When we have this, okay, you have to understand what the algebra is telling you. You need to distribute this. Okay? Distribute my x. So it gives me x squared plus 5x. And then we distribute our negative 3. So it gives me negative 3x. And that's going to give me negative 15, right? Equals 20. I think most of you are probably going to, before you write it, probably combine those in your head anyways. You get plus 2x minus 15 equals 20, right? Okay. When we do that, we generate an x squared. And when you generate x squared, you have to factor, right? And when we factor, what does the number over here have to be? Has to be 0. Okay? So I'm going to remove that from both sides. So it's going to be x squared plus 2x minus 35 equals 0, right? Okay. At that stage, we're going to factor this thing down to a product of two binomials. Okay? So it's going to get back to something that looks like that, but it's going to be different because in this one that we started with, we had 20 on the right-hand side, right? Now in this one, we got a 0 on the right-hand side. So this is different than what this one was up here. Okay, at least the stuff that's on the left. What are two numbers that multiply together to give me negative 35 and add it to give me 2? Negative 5, positive 7. And now, because we've got that thing equal to 0, we can say, if we know what that first binomial's amount is, what number can I multiply it by to get 0? Well, it would have to be 0, right? Or if I know what that second binomial is, what can I multiply it by, x plus 7? What can I multiply x plus 7 by to get 0? Well, it has to be 0. So that argument, that's called the zero product property, means that in order to take two numbers and multiply them together to get 0, that means either the number represented by x plus 5 is 0, or the number represented by x plus 7 is 0. And if we solve those, we get x to be 5 and x to be negative 7. Does that make sense? Okay. Now, if I go back to my proportion here, just think about what is really happening there. If I choose x to be 5, doesn't that thing turn into be 4 over 2? Doesn't this turn into being 10 over 5? Is that 2 equal to 2? Okay. If I choose negative 7, the first one is 4 over negative 10, and the second one is going to be negative 2 over 5. Are those equivalent? Yeah. Okay. Is that all right? Now, last class asked, well, what if I can't remember how to do that? And I get that. I understand that when you get to, like, let's say the end of course exam, and I'll give you a fighting chance to see on the end of course exam, if they ask you to solve an equation, you have no idea how to do it. Or on the ACT, and they ask you to solve an equation, you have absolutely no idea to do it. Anybody going to take the ACT in the next couple months, maybe? Okay. So we're going to have equations on there. There's going to be equations on there from classes that you won't see for another year or 2 years. So you have no chance of being successful in that. Okay. But if you understand what equations are, the fact that when I say 4 over x minus 3, I can write that as this equation. Okay. And then the right-hand side, y equals x plus 5 over 5. Okay. I just rewrite them as y equals whatever the left-hand side of my equation was and y equals whatever the right-hand side of my equation was. And I get these two graphs. Would you agree that those two graphs intersect? Let's look at this x value here where they intersect. Do you see the x value of 5 there? Let's look over here where they intersect. You see an x value of negative 7? Those are your two solutions. Okay? You see the y value here of 2. That was the 2 that I got back when we checked it, right? 2 equals 2. And then the y value back here is negative 0.4. That's the y value that we got here when I checked it. Does that kind of make sense? So whenever you're solving an equation, no matter what the equation is, if you graph it, the intersection of the left-hand side of your equation and the right-hand side of your equation, the x value of their intersection is the answer to your equation, or the solution to your equation. Okay? Last class I had one more question. It was about, this will be the last one we do. Question number 41. And I like this question. I think question 41 is something that is applicable for you, okay? I said this, I made this comment last period. Somebody said, I asked you that last 9 weeks. I think we've all maybe found ourselves in this situation where we've got a current grade, maybe we got like an 88.9 or something like that. And you are asking the teacher, do we have any more assignments? How many more points do I need to get to a 90? We've put ourselves in that situation before, right? Okay. It might not be a 90, might be an 80, might be a 70, whatever. Okay. This is how you would do that. Okay. If I know that right now I'm writing at a 340 points out of 400 total, that equates to an 85%. Okay. The question is, if there is one more assignment in the 9 weeks, how much does that assignment need to be worth if I'm going to get a 90? Provided I get 100 on that assignment. Does that make sense? Okay. So here's the idea. Think about this. If the assignment is 10 points, so I go 340 plus 10 over 400 plus 10. Does that make sense? I'm going to score 10 points, and I got 100 on it. I'm going to add 10 points to my numerator, add 10 points to my denominator. I want to see, does that give me 90? Okay. And it doesn't. It barely moves away from 85. So 350 divided by 410. 0.853, right? But it went up. Would you agree with that? So what if I go 340 plus 20 over 400 plus 20? And see what that is. So 360 over 420 would be 0.857. Went up, right? Let's try it again. Let's go. So we're seeing maybe we got to go a little bit more than by multiples of 10. Let's put, let's say I do 100. So 440 divided by 500. That's 88. That's easy. Okay, so it went up. Okay.
Pardon the interruption. This is just an announcement for all principals of food students to please pick up their leftovers in Mrs. Brayshaw's classroom before you leave for the day. Again, all principals of food students, please pick up your food before leaving for the day. Thank you.
So we don't want to play this game where we've got to do this trial and error, seeing we'll get 100, 120, 150, whatever. So what is changing, as I do these, what is changing? Do you agree that number right there is changing? Can I write 340? I don't know what it needs to be, so let's let it be x over 400 plus x, right? What do I want this to get to? I want it to equate to 90, right? Now, if you want to see it as a proportion, put it over 1. But now when I cross multiply, I get 340 plus x equals 0.9 times 400 plus x. Distribute. 0.9 times 4. 9 times 4 is 36, right? So 90% of 400 is 360. Plus then 0.9x. Subtract 340 from both sides. And then I'll subtract 0.9 from both sides. It gives me 0.1x equals 20, right? Divide by 0.1. What's 0.1? If I divide by 0.1, what's the same thing as multiplying by? I'm divided by 1/10, right? So dividing by 1/10, same thing as multiplying by 10, right? So x ends up being 200. So this assignment needs to be worth 200 points. And if you think about it, does that make sense? I think I did this in the last class, so I'll just show it to you. We started with 85 as a 340 out of 400. If I take that and make it essentially 540 out of 600, does that equate to 0.9? Okay, so that's kind of the idea. If you're at that point in a 9 weeks where you're trying to start to think, hey, how many points do I need to have left over so that I can, if I assuming I get 100% on them to get me over that bubble, that's the way you do it. That assignment, so that worksheet, not going to be due until tomorrow night. Okay. You got to go to Math Excel. There's a template that says 7.1 worksheet. Just type your answers in. The other assignment that I gave you is it's just 7.1. That is also due tomorrow evening. Okay, so the hope is that you worked on that worksheet last night, got most of it done. You got 41 now done. Okay. Work on that. Got questions over those things tomorrow. Anticipate maybe a question over question 6 or 7 out of that assignment that I gave you today.